Take a circle, drop 3 points on it, completely at random, and connect them into a triangle. Now, one question. Did that triangle catch the circle's center? This one did. This one missed. So we run it again. And again. Let the machine play a few thousand rounds, and keep an eye on the tally in the corner. It is not drifting toward a half. Not a third either. It settles at 25%. One catch in every 4 tries. Random points. A sloppy geometric question. And out falls a number that exact. By the end of this video, you'll see why it has to be 1/4, through one of my favorite arguments in all of probability. There's no calculus in it, just one idea used at the right moment. So here is the claim in full. Pick 3 points on a circle, uniformly, independently. The chance that their triangle contains the exact center of the circle is exactly 1/4. Not roughly, exactly. And this video is really about a single idea. When a random answer comes out looking that clean, the cleanness is a clue. Chase it, and you end up redescribing the randomness itself, at which point the answer just falls out. The quarter is the prize. The redescription is the lesson. Before hunting the why, let's pin down the game, because the word random hides choices. Each point is uniform, every spot on the rim equally likely, and the picks are independent. No point cares where the other 2 went. One worry people raise straight away: what if 2 points land exactly on top of each other? Or exactly opposite, with the center sitting right on an edge? Those collisions are possible in principle, and they have probability 0. 0, as in a dart hitting one exact point on a line. So we can reason about the typical case, and set the freak cases aside, honestly. Good. Now try to actually start. 3 points, all moving at once. One shapeless question. Where would you even grab it? You could try chasing all 3 points at once, and feel the question squirm away. Every point that moves drags the whole triangle with it. Here's a reflex worth stealing from every good problem solver. When everything moves at once, freeze most of it. So pin P1 and P2 wherever they happen to be. Only P3 keeps moving. Slide it around the rim and watch the triangle breathe. Some positions catch the center, others lose it. And look at where the winners live. They aren't scattered. They form one single, unbroken arc. Slide into it, caught. Slide out, lost. Suddenly the question has a shape. We just need to know that arc. Which arc is it? Well, the whole question is about the center, and the center isn't even part of our drawing yet. So let's wire it in. Draw the line from P1 straight through the center, all the way to the far side. Do the same for P2. 2 diameters, 4 arcs. Now look across the circle, at the arc directly opposite the one between P1 and P2. Claim: the triangle catches the center exactly when P3 lands in that opposite arc. Why, though? Put P3 anywhere else, and you can tuck all 3 points into one half of the circle. And when a half circle holds all 3 points, its diameter fences the center off from the triangle. Wrong side of the fence, every time. And huddling is the only way to miss. If a triangle ever leaves the center outside, you can slip a straight line between the center and the triangle. Slide that line until it touches the center, and it becomes a diameter, with the whole triangle on one side. Every miss hides in a half circle. But land P3 in the opposite arc, and no half circle can swallow all 3 points at once, No hiding place left. The triangle has to straddle the middle. Sit with this picture for a moment. It's the hinge of the whole video. And that collapses the whole problem. P3 is uniform, so the chance it hits any region of the rim is just that region's share of the rim. Length of the arc over the full circumference. The triangles are gone. The center is gone. What's left is measuring one arc. So how big is the opposite arc? Well, it moves. It depends on where P1 and P2 sit. Set them a quarter turn apart. The opposite arc is a quarter of the rim. Pull them nearly opposite each other. It opens up toward half the rim. Squeeze them close together. It pinches toward nothing. And watch the two braces. The opposite arc is always exactly as wide as the arc from P1 to P2. Its mirror image, reflected straight through the center. So the true chance swings anywhere between 0 and 1/2, depending on the deal. And each round of the game deals a fresh arc before asking P3 to hit it. So the number we're after is the average over all those deals. Averages love symmetry, so let's hand this one some. Spin the whole picture until P1 sits at the top. That costs nothing. The circle has no favorite direction. Now only P2 matters, and it's a single uniform spin around the rim. Its distance from P1 along the rim is equally likely to be anything from 0 to half the circle on either side, which means the opposite arc's share of the rim is equally likely to be anything from 0 to 1/2. And the average of a quantity spread evenly between 0 and 1/2 is 1/4. There it is. The tally from the opening was telling the truth. 25% measured, 1/4 explained. We could roll credits here. Don't let me. The actual best part is still ahead. But 1/4 is a suspiciously round number. When an average over infinitely many messy configurations lands on something that tidy, it usually means you computed a simple thing the hard way. A quarter of what, exactly? What 4 options is this problem secretly choosing between? The averaging never told us. So here's the move this whole video exists for. While solving the problem, we added 2 objects that did all the real work: the diameters. Let's redescribe the randomness so the diameters come first. To pick P1, first spin a full diameter at random. Then flip a coin for which end of it you keep. Same recipe for P2. And P3 stays a plain random point. Just place it before touching the coins. Pause the video and convince yourself this is the same randomness as before. A random diameter plus a fair coin makes a perfectly uniform random point. We rearrange the bookkeeping. The game itself never changed. So freeze the frame. 2 diameters on the table. P3 parked somewhere on the rim. The only randomness still alive is 2 coin flips, 4 outcomes, all equally likely. Heads, 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 tails, tails, heads, tails, tails. Watch the 4 triangles those coins can build. Now the observation that finishes everything. The 2 diameters cut the rim into 4 arcs, and P3 sits in exactly one of them. Each coin outcome keeps 1 pair of endpoints, and it wins exactly when P3 sits in the arc opposite that pair. Now flip 1 coin. The kept endpoint swaps to the other end of its diameter, and the winning arc swings to a different arc of the 4. Flip the other coin. It swings again. 4 outcomes, 4 different opposite arcs. Every arc of the rim claimed by exactly 1 outcome, and P3 occupies exactly 1. So exactly 1 outcome in 4 catches the center, wherever the diameters fell, wherever P3 sits. Every single time. 1 in 4. That's the entire proof. The 4 was never about geometry. It was 2 coins. Let that breathe for a second, because something sneaky just happened. The first proof asked where everything landed, then averaged over the infinite mess, The second proof, notice that once the lines and P3 are placed, the two coins already settle the question, and they settle it at 1/4 in every single configuration. When the conditional answer is the same constant everywhere, averaging was never needed. The mess was an illusion. That's what the quarter was hiding all along. Two fair coins that were wearing a geometry costume the whole time. A result you can't poke at isn't really yours yet. So let's poke. Push P1 and P2 close together. The opposite arc pinches thin, so catches should turn rare. Watch the hits. Rare. Matches. Now spread them nearly opposite each other. The arc yawns open toward a half turn, so catches should turn common. They do. And the opening simulation, run properly this time, 1,000,000 random triangles, fixed seed, 25.06%. The reasoning and the measurement agree to the third decimal. That's the good kind of boring. There's one more gift in this picture, and it ties our quarter to a shape you've known since school. Which inscribed triangles contain the center? We answered with half circles. The center gets caught exactly when no half circle can hold all three corners. Say it with arcs instead. A half circle can hold all three exactly when one of the gaps between neighboring corners opens to a half turn or more. So, center inside means every arc between neighboring corners stays under a half turn. But small arcs mean small angles. Each corner of an inscribed triangle sees the arc across from it at exactly half that arc's width. That's the inscribed angle fact from school geometry, and we'll lean on it today without reproving it. Half of a half turn is 90 degrees. So every arc under a half turn means every angle under 90 degrees. Acute. Containing the center and being acute are the same property in different clothes. And the boundary case is an old friend. Put the center exactly on one side. That side becomes a full diameter, and the corner across from it sees a perfect right angle. Thales' picture, arriving uninvited. So spin our result around one last time. A random inscribed triangle is acute 1 time in 4. Perfectly right-angled? Probability 0. Which leaves obtuse, 3 times in 4. Most random triangles are lazy, wide things sprawled far from the center. The sharp ones are the rare quarter. Let's bottle the method before it evaporates. When a random question hands you helpful objects along the way, ours were the 2 diameters, try redescribing the randomness so those objects get drawn first. If the leftover choices are symmetric, a coin, a die, 1 arc among equals, then symmetry finishes the job and no integral ever shows up. This lives in a corner of mathematics called geometric probability, where chance meets length, angle, and area. That corner is full of answers that look impossible, right up until someone redescribes the randomness. This problem is its classic doorway in. And now the cliffhanger. Same game, 1 dimension up. 4 random points on a sphere. What's the chance their tetrahedron swallows the sphere's center? Try the averaging route and you meet a genuinely nasty pile of calculus, an integral crawling over the whole surface of the sphere. This exact question once appeared on a famously hard competition exam, the kind where most people leave the last page blank. But the coin trick doesn't know what dimension it lives in. Park the 4th point first. Then draw 3 random diameters of the sphere, and flip 3 coins. 8 equally likely outcomes, and by the very same argument, exactly one of them traps the center. 1 in 8. The circle handed us 2 coins. The sphere hands us 3. And back on the circle, the pattern keeps going. Drop n random points, and the chance the center ends up inside their polygon is 1 minus n over 2 to the n minus 1. Feed it 3 points, 1/4 again. Feed it 4 points, and the whole thing becomes a single coin flip, 50-50. Why a coin flip? Find the 4 coins hiding inside that answer. That one's yours. If this scratched the right itch, subscribe. More one-question videos like this one are on the way. Got a question or a slicker proof? The comments are open. See you in the next one.